All right, guys, here is the last little bit about organic reactions. This deals with some of the more complex concepts, and we'll dabble a little bit in higher level content, which you wouldn't have been assessed on in in the regular SL curriculum that we were learning. But it's good to be exposed to it because this is some of the stuff that comes up in university and really trips people up when they take organic chemistry. So this is just maybe an opportunity for you to take a look and get a feel for how much more challenging organic can be once you finish like with the basic reactions and naming. Okay, so we are going to talk about nucleophilic substitution. I'll spend a few slides talking about that. Electrophilic addition, I'll talk about that briefly, mostly as it applies to benzene or things that have a benzene structure. And then we'll talk about organic synthesis, and then I'll describe just a little bit an assignment I'm going to leave for you for the rest of the week. So, before we start talking about nucleophilic addition reactions or nucleophilic substitution, we want to talk or do a little bit of a review of some kinetics concepts. So kinetics, which was topic 6 for us, I believe, deals with the rate of a reaction. And the thing that is most important to impact the rate of reaction is the concentration of reactants. And then the rate of a reaction can often be calculated using this rate equation, so the rate will be equal to some constant K times the concentration of the reactants. And then sometimes we end up with exponents in here as well, depending on how the actual kinetics of the reaction go down. And then some terminology here. If the rate equation for a certain reaction includes the concentration of one reactant, then we call that rate unimolecular. And if it includes concentrations of 2 reactants, then we call it bimolecular. And I'm sure you could figure out that if there were 3 reactants, it would be called what? I hope that you answered it aloud to yourself in your room. Okay, so I wanted to review this because I'm going to be using these terms unimolecular, meaning that the rate depends on the concentration of 1 reactant, and then bimolecular, meaning that the rate depends on the concentration of 2 reactants. Okay, and the next thing I want to cover, again, some just key terminology here is a nucleophile, and I'm sure given some time to think about what that word means, you would probably be able to figure out that it's something that loves nuclei. Okay, phile means love, or is a suffix that means love. Nucleo means related to the nucleus. Now, what would another molecule love about the nucleus? Well, they would love the positive charge. Okay, the nucleus has protons in it. It has a positive charge. So something that's a nucleophile, something that is attracted to the nucleus, is something that's going to be attracted to that positive charge. Okay, so this heart with the plus sign in the middle is to show that nucleophiles love positive charges. Okay, so the first type of reaction I'm going to talk about here is an SN2 reaction. Okay, so SN2 refers to a substitution reaction that has a nucleophile as the thing that's reacting with your organic compound. And then the 2 is there because these reactions are going to be bimolecular, meaning that the rate of the reaction is going to depend on the concentration of 2 things. Okay, so an SN2 reaction is a substitution reaction that happens with a nucleophile, and the concentration of 2 reactants will impact the rate. Okay, so specifically these types of reactions will occur between primary halogenoalkanes and nucleophiles. Okay, that's quite the mouthful. But we'll actually look at what is meant by a primary halogenoalkane and some examples of nucleophiles, so hopefully you'll get some more concrete understanding of what these 2 terms here mean. Okay, but like I said, the 2 here is for bimolecular, which means that the rate of an SN2 reaction will depend on both the concentration of your halogenoalkane, so your like organic reagent that you're using. It will also depend on the concentration of the nucleophile. Okay, so bimolecular because the concentration depends on these two things. So nucleophilic substitution reactions can occur with halogenyl alkanes because the carbon halogen, that's what this means right here, bond is very polar. Okay, what that means, okay, or the reason is that the halogen is very electronegative. No matter which halogen you have, they're all quite electronegative. And it pulls the electrons in the bond towards it, meaning that the carbon ends up being kind of exposed, or the nucleus of the carbon, okay? Because the halogen is taking all the electrons, then the carbon is sort of left with a slightly positive charge, which makes it ready to be attacked by a nucleophile. Okay, so this is sort of an illustration of that. Your halogen, so the X here is going to be slightly negative, leaving the carbon to be slightly positive. Okay, and then the carbon is susceptible to attack by a nucleophile, so something that's going to be attracted to the nucleus. Okay, now the next thing I'm going to show you is called a reaction mechanism, and this is definitely some higher level content, okay? If you look in the SL Chem guide, you don't have to be familiar with these mechanisms here. But I do want you to be exposed to them because I think they will come up in organic chemistry in university, which I think many of you will end up taking. So this is a primary halogenyl alkane, okay? So it's primary because the carbon with the halogen is only bonded directly to one other carbon, okay? So the same as a primary alcohol, primary means the same thing here. The carbon with the functional group that we care about is bonded to only one other carbon. Okay, and this type of reaction happens to primary halogenyl alkanes or haloalkanes because of minimal steric hindrance, okay? And that's just a fancy way of saying there isn't stuff in the way, right? Hydrogens are very small. It's very easy for something to come in and get past those hydrogens to attack the carbon, okay? Whereas if you have like a bunch of other bigger groups surrounding the carbon, it's a lot harder for another reagent to come in and attack it. Okay, so when we talk about steric hindrance, it's a fancy way of saying there's minimal steric hindrance means there's not a lot of stuff in the way for a reaction to happen, and high steric hindrance means there's big, bulky groups in the way that prevent a reaction from happening easily. Okay, so here is an example of a nucleophile. Okay, a hydroxide ion is a nucleophile because it has these unpaired electrons, which can be attracted to the nucleus of carbon. Okay, because we talked about carbon being a slightly positive pole in the dipole here. Okay, now reaction mechanisms show the movement of electrons. So there are some specific skills that go along with drawing them. So we're showing the pair of electrons here coming in and attacking the carbon. So this is our nucleophile. And then the pair of electrons here could then leave and join the chlorine. Okay? And then it mentions right here a transition state. So in theory, there's going to be this point where you've got like a partially formed bond between the hydroxide and the carbon here, and a partially broken bond between the carbon and the chlorine. Okay, so that's a transition state. It's sort of the energy maximum between your reactants and your products. And then the bond here finishes forming, the bond here finishes breaking, so you end up with a new compound. Okay, so we've substituted the hydroxyl group for the chloro group. Okay, so we have a hydroxyl group here now, and the chlorine has gone off to be an ion by itself. Okay, SN1 reactions. So S and N mean the same thing again. We're still talking about substitution reactions. We're still talking about nucleophiles, so nucleophilic substitution. But the 1 here indicates the molecularity of the rate equation. Okay, so here, in an SN1 reaction, the rate only depends on the concentration of the halogenyl alkane. It doesn't matter what the concentration of the nucleophile is. It only matters what the concentration of the halogenyl alkane is. Okay, so these reactions happen in 2 steps. In the first step, the halogenoalkane just spontaneously loses the halogen atom. Okay, so this happens just on its own without a nucleophile having to come in and push off the bromine. Okay, the electrons that make that bond, the bromine or whatever halogen is able to just pull those electrons away from the carbon far enough that the bond actually breaks. Okay, and that is the first step in an SN1 reaction, and it happens spontaneously without the nucleophile having to be involved. Once that has happened, though, so once you've formed this, it's called a carbocation, so it's a positive ion on carbon, then that is the perfect thing for a nucleophile to come in and attack. So you see your hydroxide coming in here and attacking the carbocation, and then we end up, once again, substitution product. We've got a hydroxide or a hydroxyl group forming here. However, it happened through a slightly different mechanism. Okay, now these types of mechanisms, they work mostly with tertiary halogenoalkanes. Okay, so if you look here, so this that I started with here is a tertiary halogenoalkane. So the halogen is bonded to this carbon right here, and then this carbon is bonded to 3 other carbons. Okay, so that's what makes it tertiary, as opposed to primary, which was the first mechanism we looked at, the SN2. Okay, and the reason that this mechanism works best for tertiary halogenoalkanes is because this carbocation that can be formed is more stable if there's other carbons around to sort of donate some electron density and balance out that positive charge. If you had only hydrogens in these positions, they don't have a lot of electrons to sort of move around and minimize that intense positive charge. Okay, and we call that idea of like adjacent groups being able to stabilize inductive effects. Okay, so when the adjacent groups have a lot of electron density that they can kind of help stabilize the molecule with, we call that inductive effects. And if we're talking about carbocations, a tertiary carbocation is going to be the most stable, whereas a primary carbocation is going to be the least stable because it has the fewest inductive effects. And then secondary is obviously right in the middle there. Sorry for how hideous this writing is. I definitely wrote it on a tablet, and I'm not very skilled at that. Okay, so why do we care about these two mechanisms? Why do we care about all these details? So organic chemists are often preoccupied with synthesizing products in the most efficient way possible. Nucleophilic substitution reactions showcase some of the tools they can use to optimize the rate and yield of a reaction. So you have to remember that an organic chemist is not just looking to make something, okay, make a new compound. They're also looking to make it in the most efficient way possible. So being able to distinguish between the rate and yield depending on what starting materials you use is an important tool for them. Okay, so when we're talking about these substitution reactions, an organic chemist who's planning a synthesis has sort of 3 things that they want to consider. They want to, so the halogen leaving group can impact the rate and yield of a reaction. The class of halogenoalkane, so whether it's primary, secondary, or tertiary, and then the solvent can also have some impact. Okay, so the first thing we want to consider is the leaving group, so that halogen that breaks off. The one that's the biggest is actually the best leaving group. So if you have a haloalkane with iodine, it's actually going to react in an SN mechanism way faster than one with fluorine or chlorine. Okay, and that's just because that bond, the CI bond, is long and weak compared to the CF bond. Okay, next thing to consider is the class of the compound. So you definitely, if you're dealing with a primary starting compound, you definitely want to use an SN2 mechanism. Whereas if you're or you want to induce an SN2 mechanism. My time